Hello, my name is Dr. Jonathan Jordan. I'm a lecturer in probability in the School of Mathematics and Statistics at the University of Sheffield. What I'd like to talk about a little bit in this video is about the concept of Markov chains. Markov chains are something that would be introduced in university probability courses, typically in a second year course, although it might vary a little bit according to where you're studying. In Sheffield, they are indeed introduced in a second year course. So what are Markov chains particularly about? Well, they are something which you can use where you have a phenomenon which is evolving in time in a way which we think of as random. Now, there are lots and lots of examples of things where that might apply. Things which are evolving in time, but in a way about which we have some uncertainty about the future. So I'll give a few examples here. So one, which has been particularly important, of course, recently, is epidemics. So an epidemic is something which evolves in time. It evolves in a way which is difficult to predict and has some randomness in it, according to, for example, if somebody has a disease, how many people do they then go on to infect? So that gives you the randomness in that. There are quite a few other examples, of which there are some on that slide. So there are other biological examples. There are examples from finance. And there are things like the weather. And in fact, Markov chain models of the weather have proved surprisingly useful. Another example, which isn't obviously something which evolves in time in quite the same way, is the original Google PageRank algorithm from 1998. So this is a method that Google used to estimate the quality of different web pages, so they could use that when delivering search results. And they actually wrote a paper about this, which is publicly available. You can access the paper that Google's founders wrote when they introduced the PageRank algorithm. And to understand it, one way of thinking about this is to think about a Markov chain. Okay, so what is a Markov chain? Well, we have a set of states. Now, these states are ways which we could describe where the system is at a particular time, what the current state of the system is. So at any particular time, the system will be in one of these states. Okay. And then, if we have a particular state, we have some information about what is going to happen next, what the next state of the system is going to be. And this is usually stated in the form of probabilities. So, for example, if we think about a population size, we can think about what's going to happen next. If we have, say, 65 individuals in our population at one time, then what's going to happen next? Well, really, there are two main possibilities. One is that it's going to change to 64 individuals, which could happen if an individual dies or if an individual emigrates, or it could become 66 if a new individual is born, or if an individual immigrates into the population. Okay, and we would have probabilities of each of those possibilities. We would perhaps also have a probability that the system stays the same, so nothing new happens. Okay, so that's the sort of way we would describe what happens within a Markov chain. Okay, so I'm going to try and introduce the ideas in this video by considering the game of Monopoly. And in particular, I'm going to think about the sequence of squares which is visited by a player's token. Okay? So you've got a token moving around the board, and there are 40 squares on the board. So this gives you a sequence of squares that the token visits. This can be thought of as a system evolving in time as the token moves. And so we can think of this as a Markov chain. Now, it doesn't actually quite satisfy all the rules that are needed for the formal properties of a Markov chain. However, it is close enough that we can actually get quite a bit of information about how the game works by thinking about it in this way. So we have 40 states here, which are the squares on the board. So the next few slides, I'll talk a little bit about how we think about the probabilities that we need to specify to describe Monopoly approximately as a Markov chain. So here is a Monopoly board. This is an American Monopoly board from the 1980s, but different versions are really quite similar, in particular, pretty similar mathematically. So we don't need to worry too much about the differences there. So the player's token will always start on go. And then we roll 2 dice, and the sum of the numbers on the 2 dice tells us how many squares to move. So, for example, you will know that the probability of rolling 12 on 2 dice, getting a 6 on both dice, is 1 over 36, assuming the dice are fair and so on. And so if we get, with probability 1 over 36, we move 12 squares, which takes us to the electric company on the left-hand side of the board. And you can see here that I've drawn on the board some arrows which represent the different possibilities, different possible squares that the token can move to from go. Okay, so in particular, probability 1 over 36, we move to the electric company. The most likely square for us to move to is the one which we would get if we roll 7, because that is the most likely sum of numbers rolled when we roll 2 dice. And that would take us to the chance square, which is the purple question mark, a little bit left of the bottom centre there. If you look carefully, you can see that I've written some numbers on there, which are those probabilities, the probability of making each move starting from go. Okay, so this is what happens when we start from go. Now, if the only thing that happened in the game of Monopoly were just rolling pairs of dice, so that it was always the case that we just rolled a pair of dice and we moved the number, the next move was the number of squares that are shown on the dice, then it wouldn't really be very interesting thinking about Monopoly as a Markov chain. It wouldn't, from a mathematical point of view, be a very interesting Markov chain. However, Monopoly is not like that. There are other things that can happen as well, which tell you with the sequence of squares that your token visits. So perhaps the most obvious example is the go to jail square in the top right. If your token lands on go to jail, then it must go to jail. So that takes you from the top right, which is 30 squares from go, to the bottom left, which is 10 squares from go as you go around the board clockwise. Okay, so that is one thing that can happen, which is not just to do with rolling dice. Now, another thing that can happen, which has some interesting effects, which we'll probably discuss in the tutorial, which is that you can land on a chance or community chest square. So if you land on one of those squares, for example, the one I just mentioned on 7 squares from go, you have to draw a card. Now, some of those cards don't tell you to move anywhere. They tell you to pay lots of money to the bank or whatever. But some of them tell you to make a move. And in the photograph here, you can actually see 4 of the cards, again from the 1980s American edition, which tell you where to move. So, for example, if you look at the bottom right, one of those orange cards, it tells you to advance to St. Charles's Place, which you can see is the square 4 along, the just first one after jail. So if you land on the chance and you then draw that card, you have to move your token to St. Charles's Place. And there are various other examples of these cards which tell you to move, which you can see in that picture. And we can see some of the moves that they suggest drawn again as black arrows on that picture. So these are some of the things that can happen when you draw a chance card. So if we land on a chance card, the probabilities become a little bit more complicated. So on this picture, we can see again that we have some probabilities. And so, for example, the probability of going to the boardwalk on the right is now 1/16, because there are 16 cards, one of them takes you to boardwalk. And that's similar for some of the other moves on here. There are also places which you could have got to just by rolling 2 dice. Now, the probabilities are now smaller for those than they were from go, because we might have to draw a card which would tell us to go somewhere else first. And so the denominator, in fact, is now 96 instead of 36. So the probability of moving 12 squares to the one just before 3 parking in the top left there is now 1 over 96. Then there are some which we can get to in two different ways. So if you look at, for example, at St Charles's Place or the Electric Company, if you look carefully, you can see I've drawn two arrows from the chance card, chance square, pointing there. And to work out the probability of making one of those moves, we just add up the probabilities we get in the two ways. And you can see the sums on the squares there telling you what happens. So we can do something like this for every square on the board. We've seen the ones from Go and from the chance, 7 from Go, and I've mentioned what happens from Go to jail. And we can put this together in a picture which describes all the possible moves that can occur for a token in a Monopoly game. And it also indicates here the probabilities of these moves. So the thickness of the lines indicates the probability that you make that move if you're in the square where the arrow starts. So obviously the one which has the highest probability, probability 1, is the one where we go from Go to jail, square 30, near the bottom of the picture, to jail, square 10, near the top of the picture. So that's the thickest line because the probability is 1. There are also some thinner, much thinner lines. So for example, the ones where we're just talking about rolling 2 dice and getting a 12, probability 1 over 36. So if we look at some of the thin lines, which seem to be making that circle in the middle of the diagram, those correspond to those much lower probabilities. And we can see some scattered ones going across the middle of the diagram. Those are moves that chance and community chest cards are telling you to make. Okay, so this diagram describes all the possible moves in a Monopoly game, and by the thickness of the lines, describes their probabilities as well. Now, what I'd quite like to get you doing is to do some calculations with a simple Markov chain. Now, the full Monopoly game is really a bit too complicated to do this at first because there are 40 squares. We need to think about probabilities for lots of different possibilities, and to do calculations by hand becomes very messy. In the tutorial, I will show you some calculations done by a computer, which gives some information about what happens in the full Monopoly game, which is analogous to what I'm actually now about to talk about. So what I like to do for these simple calculations is to think about what I call post-apocalyptic Monopoly. So for post-apocalyptic Monopoly, all the properties, the utilities, and the railways have gone. The only things still left are the Go square, need someone to start, jail and Go to jail, and in this world you can still park your car for free. So those are the possible squares we have left. Because I've now only got 4 squares, this idea of rolling 2 dice and potentially moving 12 squares is a bit too complicated. So in fact, I'm actually just going to assume that you toss a coin. If you get heads, you move 1 square, and if you get tails, you move 2 squares. However, Go to jail is still going to play exactly the same role it does in standard Monopoly. So if the token lands on Go to jail, it goes to jail. So that's still going to have probability 1. Okay, so the calculations I'm actually now going to do are with this post-apocalyptic Monopoly rather than the full game that I was describing earlier. Okay. So let's actually do some calculations to introduce you to the idea of how we might do some calculations here. So we have 4 squares: Go, jail, free parking, and Go to jail. And we can think about the probability that we're in on a particular square. And so we have 4 of these probabilities, and we can write them like this. We have 1 representing the probability of being on Go, 0 for jail, 0 for free parking, and 0 for Go to jail. That represents the idea that we start at Go, so we have us there with probability 1, we're certainly there. We can't be on any other square, so the probabilities of being on any of those other squares are 0. So that 1, 0, 0, 0 represents certainly being on Go. So that represents the starting position. At the bottom of the slide, you can see what happens after 1 move. So after 1 move, heads takes us 1 square, which is to jail. So that happens with probability 1/2. Tails takes us 2 squares, also with probability 1/2. to free parking. So the probabilities are now half for jail, a half for free parking, and 0 for the other two possibilities, which we can represent again in this row vector style as 0, a half, 0. Okay, so that's our first step. So let's now think about a couple more steps. So remember the vector at the bottom there, 0, a half, 0. So let's think about the next step. Well, with probability of half, we were on jail. If we were on jail, we move to free parking with probability of half and to go to jail with probability of half. Because I'm thinking about the sequence of states we visit, we do include go to jail. Even though we know that the token will move immediately to jail, we do include that as one of the squares visited. So that means that if we start from jail, the probabilities are 0, 0, a half. Similarly, if we start from free parking, which we also do with probability of half, the probabilities for the next step are going to be a half, 0, 0, a half. And so what we do, using the standard rules of probability, is we take those vectors and we multiply them by the probabilities of actually having started there in the first place and add what we get together. So we get a half times the vector from jail plus a half times the vector from free parking, and we add those together and we get the vector on the right there, a quarter, 0, a half, a quarter. We can now do the same thing for another step. So now with probability a quarter, we were back to go again. So we get a quarter times the vector from go, which is 0, a half, 0, plus a half times the vector from free parking, which we've already seen as a half, 0, 0, a half, plus a quarter times the vector from go to jail, which we haven't seen yet, but from go to jail, we have to go to jail. So in fact, that is very simple. It's 0, 1, 0, 0. Okay, so there are 3 vectors now to add together. In general, there would be 4, but the one from jail itself is missing because we had the 0 in the previous step. And if we do that, we now get the probabilities at the third step, which is now a quarter, 3/8, 1/8, a quarter. Okay, so hopefully you can start to see how you do these calculations. Okay, and we can actually do this in a more generality. We could assume that the probabilities at one step were A, B, C, and D, for example. And then we would get A times the vector from go, plus B times the vector from jail, plus C times the vector from free parking, plus D times the vector from go to jail, which is just 0, 1, 0, 0. And if you look at that, you can see that those at the next step, in general, take the forms which appear there. So, for example, the probability of being at jail at the next step is D plus A over 2. That's because with probability D, we were to go to jail and just had to go to jail. With probability A, we were to go, and then a heads in a coin toss takes us to jail. So that gives the A over 2 that appears there. So that's why you get D plus A over 2 as the second entry there. And you can work out the other entries in the same way. Okay, so I'm nearly at the end of the introductory video. So in the tutorial, we'll think about how this actually evolves in practice. What happens when we start from a particular starting point? So the obvious starting point is the 1, 0, 0, 0 thing I mentioned, starting from go. However, you can get some intuition about this by thinking about starting from some other vector of probabilities. So these need to be vectors of probabilities, so they need to add up to 1. One possibility is that, for example, you could roll a dice. If you get a 1, 2, or a 3, you'll start on go. If you get a 4, you'll start on jail, 5 on free parking, 6 on go to jail. So that gives us the vectors in the probabilities in that first example there, a half, a sixth, a sixth, a sixth. And you can come up with other ways of starting, for example, the other 2 that I've suggested there. So what we'll do is we'll think about how this is actually going to evolve over a long period of time. One thing you might actually like to try doing is to code this. If you like coding, you could code this and see what happens long term that way. I'll also talk about what happens for real monopoly. So doing this, we'll get some information about this post-apocalyptic monopoly and what that tends to look like in the long term. But we can, in principle, do the same thing. As I say, I'll show you what happens for real monopoly. And perhaps I'll also talk a little bit about Google PageRank, which I said was another example of a Markov chain, and some of the other examples that I mentioned at the beginning of the video. Okay, so thanks for watching, and hopefully I'll see you at the tutorial after this.